Dear students, in this video we are going to discuss about how to perform deformation and stress analysis on a cantilever stepped bar using ANSYS APDL software. Okay, so this is the problem given in the problem. Actually this problem has been taken from a textbook, so the units are not an SI unit format. Okay, so no problem, we can convert the units into SI units. So 0.9 inch square, 580.644 mm square, 0.3 inch square, 193.548, and we can convert the unit kips to Newton, inch to mm. Okay, so the problem is like this. Okay, so here the entire structure has been made up with 4 nodal points A, B, C and D. So in between A and B the first element has been defined, between B and C the second element, and between C and D the third element. Okay, so the elements AB and BC, the elements AB and BC are of with uniform cross section 580.644 mm square, and the element CD is of cross sectional area 193.548 mm square. Okay, so to model the entire structure in the ANSYS APDL page, we have to create 2 different section IDs because the entire structure is made up with 2 different cross sectional area. Okay, so AB first element, BC second element, and CD third element. The nodal points, point 1 that is A, point B 2, point B C 3, and point D 4. So totally there are 4 nodal points and 3 elements constitute the entire structural element. So now we will discuss the step-by-step procedure to solve the given problem in ANSYS APDL page. Okay, go to preferences, select structural, preprocessor, element type, add, edit, delete. As a given problem as a bar element, so we can select the type of element as link. Material properties, material models, structural, linear, elastic. As the considered material of the given bar element is steel, it is of isotropic type. 2 10 power 5 Newton per mm square. Poisson's ratio value will not influence the deformation and stress result, so we can set it as 0. It will not influence the results. Then sections. So the considered structure of the cantilever bar is made up with 2 different cross sections, so we have to define 2 different section IDs. So the section ID 1 can be considered to represent the elements 1 and 2 of cross section 580.644, 580.644, 580.644 mm square. Apply. So now we can create the second section ID whose cross sectional area is known to be 193.548. Okay, so now we can model the structure using nodes and elements. So nodes in active CS, so the first nodal position can be considered as the reference. So the nodal position coordinates for the first nodal point as 0 0 0. Okay, apply. Second nodal point, it is the entire structure is distributed along the positive x-axis. The second nodal position is 304.8, 0, 0. Okay, naught 4.8, 0, 0. Third nodal position 6 naught 9.6, 0, 0. Fourth nodal position from the reference point 1016 mm. Okay, so we have defined all the 4 nodal points. Now we can join these nodal points to create the elements. Okay, so for that we have to go to element attributes. Now we are going to join the first 2 nodal points. So for the first 2 nodal points connects the element AB. So the element AB is of the cross section representing the section ID 1. Okay, so after selecting the section ID 1, go to auto numbered through nodes, click the nodal points 1 and 2 and apply. So already we have selected the section ID 1. We know that the nodal points 2 and 3 as representing the element BC. So element BC is also having the same cross sectional area of element 1, 2. So directly we can click nodal points 2 and 3 and click OK. Okay, but the element joining the nodal points 3 and 4 is of different cross section. So we have already defined that cross section in section ID 2. Okay, so go to element attributes before joining the nodal points 3 and 4. Change the section ID as 2. Okay, now we can go to auto numbered through nodes, click the nodal points 3 and 4. Okay. Okay, so then go to solution, define loads, structural, apply structural displacement on nodes. In the problem the first nodal position is fixed, so click the first nodal position, select all DOF and OK. So now we have fixed the first nodal position. So then we have to define the loads at the respective nodal positions. So the second nodal position is loaded with a magnitude of 333,616.62 Newton in the positive X direction. On nodes, click the second nodal point. Under force or moment, on nodes, click the second nodal point. OK. Fx. So the force value is 333,616.62 Newton. OK. So then the third nodal point is loaded with 200,169.972 Newton in the negative x-axis direction. Okay. So click the third nodal point, Fx minus 200,169.972 Newton. Okay. Then the fourth nodal point is loaded with 133,446.648 Newton in the positive x-axis direction. Fx, the value is 133,446.648 Newton. Okay, so now we have completely defined the problem. So now we can solve the problem. Current load setup. Okay, solution is done. So to read the results, go to general post processor, plot results, contour plot, nodal solution, displacement vector sum. So this is the deformation plot. So the maximum deformation experienced by the cantilever bar under the loading condition is 1.9264 millimeter. Okay, so we can note the deformation experienced by each and every section of the cantilever bar from the deformation plot. Okay, to read the results exactly at the generated nodal position, go to list results, nodal solution, displacement vector sum. So along x-axis the deformation is experienced in the respective nodal positions can be observed from the table. To read the stress results, go to element table, define table, add. So the sequence number for representing the or for finding out the stress results, axial stress results in the ANSYS APDL page, the sequence number LS1 to be defined first. Okay, then go to plot results, line element results, LS1. Okay, so this is the stress result plot. List results, element table data. So from the list results table, so we can exactly identify or noted down the stress induced in the each element we have considered. So the first element we have generated has experienced tensile stress of magnitude 459.65 Newton per mm square. The second element we have generated has experienced compressive type of stress of magnitude 114.91 Newton per mm square, and the third element, that is CD, has experienced 689.48, that is tensile stress Newton per mm square. Okay, so this is all about the problem. Thank you.